Hello, this is Brett Henney. This is my demo for my Intro to AI Spring 2014. My project is AI Cooperative Pathfinding. I'm evaluating A, Dijkstra, and various heuristic methods. So let's just get started. I wrote the software in C#. I did a model view controller architecture. This is the main UI. So first I was going to go over the features in the main UI. So there's a few sections, AI parameters, where you can select the algorithm, A* or Dijkstra, the heuristic method. For A*, you have the option of these four: Euclidean, Euclidean squared, Manhattan, or Chebyshev. If you go to Dijkstra, you don't get any options because Dijkstra doesn't have a heuristic. You can set the field of view of the agent, which represents how many nodes from the agent's current location that it can see. The method the next field is the method that is used to calculate the field of view nodes. Euclidean distance, same as before, Euclidean squared, Manhattan, or Chebyshev. These are available for both Dijkstra, and they're not algorithm specific. If you have multiple agents on the map, if you want to enable agent cooperation, it's done here. This helps generate the map. You can change the map size, the percent walkable, and the number of agents. So if you wanted to generate a random map with one agent, size of 25, you can just click that. If you want the map size to be smaller, you can click that and automatically adjust everything accordingly. If you want to increase the number of agents, you can just increase the number of agents. So for this one, let's just do an empty map 25 with one agent. The preferences are, if you have multiple agents, this will be populated with agent 0, 1, 2, 3, or 4. So if you generate 3 agents, the viewable agent, you can select which one you want to view. Otherwise, it gets very confusing on the map to see all these agents moving. Persistence is basically if you want the path to be persisted as the agent moves. Visualizations allow you to evaluate how the algorithm's evaluating each node. It puts a light red, pink color if the node is put into a closed or visited list, depending on the algorithm, and it paints the node green, light green, if the node is still in the open list or the visited list in terms of Dijkstra. Max steps. If the path cannot be found, if the finished node is completely surrounded by walls, non-walkable nodes, this will allow the algorithm to basically fail without sitting there forever in an infinite loop. And these step delays allow you to slow down the simulation so you can actually view it. The control section will start the simulation. This can reset it, and then this map node editor allows you to change the position of the start and finish nodes by using the start button or the finish button. So for like this one, if it highlights green, the help section down here says click map to change the agent 1 start node. So I can click, I can move the agent 1 start node. If I wanted to change the red agent start node, I can do that. And same with the final. Move the green final, move the red final, and then move the blue final. The map node editor also allows you to draw walls. So you can click one at a time, or I've also added a feature where you can just drag and just create maps any way you want. All the data is logged. It's not all the data is stored in this table over here, and basically will tell you the agent ID, the map ID, field of view, steps, visible nodes, visible walkable nodes, visible non-walkable nodes, evaluated nodes node evals that were performed, how many nodes were shared, possible nodes in the map, whether it was a success or not, the algorithm used, heuristic method used, field of view method, if agent cooperation was enabled or disabled, the size of the map, percent walkable, and the number of agents. All this data can be exported to a CSV and cleared as well. So let's just do a first example. Let's create a simple one or an empty map with one agent. So if I wanted to do A* with a field of view of 2, I can just run that and it'll calculate it. I can then add walls, say add a wall there, and it would solve this. The black nodes represent nodes that the agent cannot see. It's based on the field of view. So if you increase the field of view to twice what it was, you'll see a little bigger field of view. And if you notice here, because it can see more, it realizes that this is a better path. If you increase it even larger, then it can see more and there could possibly be a better path. So if you close this up, it'll go like that. You can also, so let's go back to a field of view like 3. Heuristic methods. So you can try out different heuristic methods. So there's Euclidean squared, and they should give you very similar results, especially for this map. So let's make it a little more complicated and like run that. And the movement of the agent can go through diagonal. So you see here it cut through a diagonal. So if you don't want that, you just close these diagonal paths up, and you can run it again, and it'll find the node. You can also, I've added a feature to help evaluate these AI methods with this visualization tool here. And sometimes it's beneficial to put a delay in there so you can actually see how it grows. So the way the agent works is all these nodes are being reevaluated because it can't see the walls until it actually enters the field of view. So as this agent moves, it's discovering all these walls. And anytime a non-walkable node is entered, that means the entire algorithm has to be reevaluated because the map has changed, which is one of the things that I'm trying to evaluate with field of view. Anyway, this is going to take a while with this delay, so I'm just going to cancel this out and lower the delay to 0. So you can see the visualization going on there. And now if you increase the field of view to a larger value, then it does less evaluations because it can see more of the map and it can make a better determination. So instead of going down here like it would want to, there's actually a path here that was a lot faster. If you generate a random map, you can see the same thing. So the next thing is map size. If you want to do a map size of, 5, you can generate an empty map with 5, and you can calculate it this way. You can move these around. You can turn the visualizations off. You can increase the step delay so you can actually see it traversing through the graph. If you're doing a very large map, the larger the map, the longer it's going to take sometimes, obviously, to do this. So if you do a field of view of, if you're generating a map of 50, you got to give it a second. It'll generate the map. And it will start traversing through the map. Let me lower the delay here so it doesn't take so long. And you can see how the field of view increases as it goes. All the data is logged over here, so all this data could be analyzed. So let me go back down to a map of 50. Next thing I want to show you is agent cooperation. So you can generate a map with 2 agents, and you can move them around such that they cross paths. So if agent cooperation is disabled, they just go to their paths. If you only want to see one agent, you can do that. You can still see the other agent traverse. You can see it probably a little better here as it goes through, but this agent is the only one enabled. If you want to turn the agent cooperation on, once the agents enter the field of view of the other agent, they would converge. So let's put all these on so you can actually see them. So right here, they entered field of view and they actually diverge to meet and share map information. Once they do that, every map that's in each of the agent's maps are then shared. The data log will then show that as well. If you look at the shared nodes, like up here, we did a couple runs where they were shared at 63. This thing, if you sort by, this table can also be sorted by map ID, field of view, so it's a sortable table. You can export all this to a CSV as well. So if you hit export, go to desktop, and I can save it as test run and overwrite this data, and then you can open up this data in a CSV file and evaluate it later. And it gives you all the simulation variables, so you can always recreate it. You can tell if they've used the same map, if multiple simulations use the same map by looking at the map ID. So let's close that out. And you can also clear the list. As soon as you clear the list, it's gone forever. So that is about it for the demo. I hope it was very informative, and thank you for watching it.